My pleasure to introduce next our keynote speaker for this session, Jared Roesch. Jared is a distinguished engineer at NVIDIA, where he builds AI systems and compilers for NVIDIA GPUs. Before that, he was co-founder and CTO of Octo AI. Jared earned his PhD from Paul G. Allen School of Computer Science and Engineering at University of Washington. So please join me in welcoming Jared Roesch.
Hey, all. Good to see everybody. So today I'm going to talk a little bit about evolving the programming model for the GPU. My title is a little bit of a pun on the shape of things to come, given that we're talking about the shape of arrays. So today we're going to cover kind of high-level agenda to go through is also feel free to if something's unclear, feel free to shout out, ask a question. I'm happy to expand as I go. Really, what we're going to start first with is why we're evolving the programming model, and what I think the most important question of all programming models are, what are we trying to abstract from the user, for the user. We're going to talk a little bit about this in an instantiation of CUDA TileIR. We'll talk about this then being exposed as a programming language, DSL if you will, to end programming environments. And then we will talk a little bit about performance and kind of some of the future work, including interop with existing code and where we're going from here. So to start off, kind of historical perspective, right? It's worth remembering the GPU is a GPU for a reason. In the 90s, it started with, we've got fixed function accelerators, roughly, your rendering API, every single function that you would write would have a corresponding piece of hardware behind it that would then execute that function. Over the 90s to 2000s, things started to evolve quite a bit. People started to ship programmable shaders to give people the ability to control the behavior of the GPU. What this eventually evolved into is now, where CUDA, the well-known, NVIDIA programming abstraction debuted was in 2006 when we moved to this unified architecture. And a lot of this was about taking what people were doing by hacking it in the GPU days and also trying to unify both the hardware and on the shader side and the compute side so that you can do more uniform hardware scheduling. So there's like one big hardware innovation that opened up the programming model here. Now, roughly since then, for the last 20 years, it's been accretive, right? We're like adding new abstractions, new programming APIs, there are cooperative APIs, there's sort of new things growing all the time. But as we've gotten to, let's say, Blackwell, which is the most recent, soon-to-be previous generation of NVIDIA hardware, the hardware looks very different than it used to. It is not the same machine that kind of gave you this very, I'm putting in quotes, simple SIMT abstraction where each thread was executing and they were in lockstep and you could kind of run your compute in any way that you wanted and you're kind of processing over parallel points in a very regular way. Things have changed a lot. Part of the reason why is that for every generation we've been giving people new tools to both write more complicated programs, like sort of the general purpose part of the GPU programming has actually grown quite a bit, even from 2006. You can do a lot more than you used to. Even random new things that are happening where you can initiate storage operations now from the GPU. This is just totally out of band for my talk, but you're getting to this point where there's more and more functionality for writing general purpose systems that execute on the GPU. I think the challenge is by the time we get to Blackwell, the number of tools have grown quite tremendously. One thing that's happened is the sort of single program ordered thread abstraction that's synchronous is falling apart. As kind of touched on in many of the previous talks or Mary's other keynote, things are more and more asynchronous today. And this is breaking the programming model that we have in quite a few ways. So one way that we think about the programming model is just like a simple taxonomy is to break it down into sort of three tiers of programming model. There's what we sometimes refer to as grid level. This is the PyTorch, NumPy, kind of APIs. Like I have a tensor in memory, I tell you what I want to do with it, you manage all the resources, you compute the result for me, you store it for me. Then there's the thread level model, which is what you know and love. You can control each individual thread's behavior, but you have to do a lot of work to coordinate the program. In the last few years, there's things that sort of in this intermediate abstraction, popularized by Triton. There's sort of this tile level programming model. Obviously, this comes in many other flavors. There's flavors of this in Halide and TVM, and there's a million systems at this level. But what's different at all of them is that in the top level in the grid, the system controls all the partitioning of work. Like the user just gives me some data, you tell me what you want to do. Some sufficiently smart system or compiler or set of pre-written kernels goes and executes. At the thread level, you control everything. And what we want to end up in the middle is that the user does some logical division of their work into blocks or data tiles, and they then give the system the ability to control the final mapping onto low-level hardware resources. So you can see instantiated this is the grid level is things like kublas or PyTorch. The thread level is CUDA C++. Tile level is what we're going to be talking about today. So the most important part in the programming model is what do we abstract. So historically, for those of you who don't know, NVIDIA has always had an abstracted programming model. You don't actually directly write the instruction set. So when you write an NVIDIA program today, you generate ptext. Ptext is that actual virtual ISA for the hardware. And the driver JIT compiles ptext to your actual target hardware on the fly when you actually go to execute a kernel. A lot of this backwards compatibility and abstraction really was motivated by graphics, but it's actually been extremely useful just as a general portability layer. The problem is that the ptext abstract machine is made a bunch of choices already. For example, every logical thread in ptext has already been scheduled. You know what every logical thread will be doing ahead of time. So what happens if you, for example, move a kernel from a system that has some number of thread configuration to another one? Simple kernels like element-wise, this is fine. This becomes more of a challenge as we move into the new world that we've started to grow into, where you have cooperative operations where many number of threads or system resources have to be donated to a computation like an MMA, and now you actually can't move that program from chip to chip anymore. It is now completely architecture specific. So what we want to do is actually up-level the programming model. So what we've done is we're moving from where your unit of execution in the old abstract machine is a thread, to now you operate on a block. So the idea is before you had a grid of thread blocks. Each thread block have some number of warps running inside of them. Each warps have a number of threads. We've consolidated this down into one level of hierarchy. So you're going from this multiple level of hierarchy to one simpler level of hierarchy. Then on the data side, what we've done is we've gone from you computing on a single element or a small set of elements at a time in an individual way to working on aggregates. So each tile block executes on a tile. So before, if you had 8 vector values that you were given to each thread, now I'm going to get a tile of 8, and I can compute on it directly. And what happens is, the real challenge that we talked about on the previous slide is, how do we do the decomposition from my image into these tiles to individual regions that I then work on? And the problems today can be categorized into a few different flavors. One is what we were talking about in Mary's talk and others is, where do I store the tiles? There's multiple levels of memory scope that I can put them in. Today we have obviously registers, you have shared memory, you've got global memory, now you have TMEM in Blackwell, and it's likely that the number of memory elements are continue to change and grow over time. There's a question of what layout do you put them in. So depending on what computation or sequence of computations you have, computing the optimal layout is something that's really challenging for a human programmer, especially as you're changing the program around it. Another big problem is, what is your memory movement strategy? So in order to feed the really big compute engines we have, you need to pipeline memory so that you always have more memory operations happening in the background, so you're ready to compute every time, so you can try to actually reach sort of that roofline performance of the machine. So there's many different strategies, and it's only gotten worse. Before it was roughly just synchronous loads, from one memory scope to another. Now we have asynchronous copy engines. We have the TMA, which is a multi-dimensional DMA engine, which allows you to describe a volume, an outer volume, and load subregions from it via queries. But it has many complexities, like the descriptors for it need to be allocated on the host device. It has restrictions like the strides and shapes are not actually 2 to the 64, so you have to make sure that you meet the alignment criteria. So like already you can see, you start to pull in this thread. It's not just, oh, I'm going to replace it with a copy here and everything works out. And it has different latencies. So actually for small sizes, it's not good because you're sort of paying this batch transfer speed versus incremental copy. And so you can see people actually want to turn this off sometimes. So it's not just like I have my magical hammer and I will fix every problem in my program. And then finally, the compute strategies. Once I've got the thing in some kind of memory, I have a lot of different instructions to compute on it. And which ones do I use? So in the old world, all of these are your problem, right? What we want to move to, as I've been describing, is that we want to take away some of these problems for you because we believe they're hard for humans to solve. So memory movement, compute strategy, memory layout, storage, and many others. And importantly, we want people to be able to guide this through a system of hints and directives that are higher level than rewrite my C++ code every single time a new chip comes out. So what we've done in order to do this is we're introducing a sibling virtual abstraction to PTEX. So TileIR itself also can be viewed as a virtual instruction set. It's actually understood directly by the driver on the NVIDIA GPU driver. So you can take a TileIR bytecode, you can upload it to the driver with one of the launch APIs. Everything works like normal. I'm going to show you a little bit of that more in my talk. But importantly, it provides a stable, portable way to program the tensor parts of the hardware. So you can kind of imagine there's some Venn diagram of some programs you can write in SymT or Tile, or a kind of concentric circle Venn diagram. But there's some programs in SymT that are not well expressible in Tile today. So that's actually an important call out, is that we want to restrict the semantics of the program. So for example, if you want to write a hash table, it's not really a great language to write a hash table, like a concurrent GPU accelerated hash table. But that's by design. And we're positioning it really just as PTEX. It's another part of the platform. So here's like a cartoon of what the compiler stack looks like today. And I'll talk a little bit more about that. So really the goal here is this is one graph without hand tuning. This is even just tile dimensions. We want to be able to take a program across A100, H100, the RTX is the consumer cards, which importantly have different microarchitecture than the server cards. And then B100, B300. And each one of them actually, many of them have different tensor core shapes. So that's another thing that's starting to happen, is in the world of heterogeneity, even the homogeneous nodes that we have are not so homogeneous anymore. They're actually kind of heterogeneous. We kind of have heterogeneity just even in the Blackwell generation, because there's multiple different parts and they have different configurations. And we've mostly been able to achieve that so far. It's like, that's what this graph is, just one piece of data point. I'll talk some more about the performance numbers later. So one thing I just want to talk about a little bit is contextualizing this in the bigger change that's happening, is that one thing that I think is useful for the PLDI community is that I've been doing this, working this kind of thing for 8 or 9 years at this point, and for a long time the GPU folks have been really resistant to fully moving to compiler-driven solutions. There's still a lot of code written by hand. I think what's happening in mass inside of the company and maybe across the industry is that we are driving more and more compiler-driven solutions. So there's actually been a big shift where the architecture inside of NVIDIA is really consolidating around shared intermediate representations and shared compilation stacks so that we can reuse these bottom-level components. So here's like a little diagram of what it's starting to look like. The idea is that there are multiple programming model exposures in different programming languages. So you can see here I have in SymT, in C++ now, there's a way to spell both traditional C++ NVIDIA code, CUDA code. Also, you can now write tile functions. We have, obviously, Cutlass C++ is like a library version of this. But Cutlass has also been building compilation-driven technology for the last few years. So now in Python, you can use NumPy CUDA, which is an existing programming layer for writing SymT-style code in Python. You can use cuTile, the new DSL. And then you can also use Cutlass Python stack, which is the Qt DSLs and friends in order to program it. Each of these kind of have a different flow. So for example, the SymT code today directly goes through our LVM stack into PTEX. The tile flow goes through TileIR. We now have an MLIR-based compiler stack that's on top of it. And then there's an architecture-specific, non-portable flow on top of Cutlass, which you can use to program a specific GPU with all the architectural details exposed to you. And what this is looking like is that we can share all these components, and we can give people different programming experiences, but we actually can share more of the infrastructure, because I think, even to Mary's point about the industry across companies being fractured, it is fractured even inside of NVIDIA. I don't have a slide here, but I made one when I first started with one of my colleagues that had like 35 different ways to write kernels for the GPU, just inside the company. And it's not even complete. There are more. So really, the goal here is to make all of these pieces more reusable, so that part of what we believe is that much of the DSL or the programming model, like at the DSL programming model level, innovation has occurred in the community. So we want to make these things standards that people can build tools on top of or do research on top of. So you can see actually like third-party languages. There's a prototype from NV Research. Actually, there's a paper now in arXiv if anyone wants to read it on how mapping Rust to TileIR. The Julia community wrote their own version that maps Julia onto TileIR. And we have a backend that we wrote that takes Triton and compiles it to TileIR. And we really wanted to be an opt-in component for many of these as a backend that they can use for things like Triton, for example. So also just in general, there's been a cleanup and a consolidation of a lot of the compilation technology into standard stacks. So like we've been moving as a greater company, greater organization to more upstream-driven LVM and MLIR development, which is, and the reason I wanted to talk about this is I think this is part of the cultural change and the driver of some of this programming model innovation is that with these shared stacks, building these shared programming models with shared lowerings, give us the ability to do a lot more joint optimization across the whole stack, which is becoming more and more important for the use cases that people care about. So with that, I'm going to talk a little bit about the DSL exposure on top. So I'm going to use this kind of to drive the explanation of TileIR as a programming model abstraction. So cuTile is our branding name for the DSL to kind of differentiate it from the intermediate representation. We initially released cuTile Python, which is open source. It's a DSL you can find on GitHub. But we've been using the name as also for the C++ exposure and the Rust exposure and other ones. Today I'm going to mostly talk about Python. So here we'll start. So here's like a very simple kernel. And you can see that it exposes a NumPy-esque programming model where instead of computing on entire arrays, though, you can compute on fragments at a time. And we're going to dive deep on this in a moment. The important part to see, though, is that you can see that the kernels are pretty concise. So this one here on the right is half the size of this really naive SymT kernel, which will not produce very good performance on the GPU. Because all the things I talked about are present here. Like you've committed to some, for each thread knows exactly what it's doing. You have concrete loads and stores. You've committed to one compute strategy, one tiling, one loop strategy, et cetera. And you even have the synchronization right there in the middle. And you can see that here is the speed of light non-portable Cutlass code, which is compressed from if you wrote it by hand. And I think I know how to write GPU code, but writing high-performance Cutlass code and reading it is very hard, to be frank. And so these, as you'll see later, are roughly equivalent in performance. So now I'm just going to kind of go example by example to explain some of the programming choices that we made. So one, you can see here highlighted in yellow, the global arrays are mutable and accessible by logical blocks. So here, this softmax kernel takes in a global input array and a global output array. It loads a tile that it shapes. The second argument here is the shape of the tile that I like to load. And then I am going to compute some functions over it. I'm going to store it back. One important thing to know, though, is here is the index on which I want to load. Here is the tile size, which I load by. And then once I've loaded a tile, tiles themselves are values in the programming model. So they have no ascribed memory location, and they are computed on immutably. So you can see here highlighted in green, when I compute max or exp or subtraction, sum, division, all these are producing new values. So each one of these is going to become a new value. And if I want to persist that to memory, for example, I need to perform a store. Store is symmetric with load. In this case, based on the shape of the tile, I'm going to store viewing it as a collection of those shapes with that index. So roughly the load and store APIs allow you to view any global array as a bag of tiles of a certain size, and then you can index them like normal with normal coordinates. So you can see to that point, if you don't store it, maybe I made a typo here. You need to compute because if you, actually this is what I want to say. If you override a binding like this, for example, in the DSL, it actually is just shadowing the binding. It doesn't actually update the value. There's no updates being done to the tiles at any moment. One important thing, like I said, is that we've done a lot of work to make this part of the platform, if you will. Like everything is integrated. So tile kernels are launched with the same underlying API as the SymT kernel. So in this case, you can write device code here. So this is a cuTile kernel. You can, same one we just talked about. And then you can, on the host, for example, move an array to the device, allocate an output buffer, call the launch API on the kernel with a grid size, you pass the inputs and outputs, and then you can copy the result back to the host. And this is just like exactly what you would do in a normal GPU kernel, but just all in Python. Importantly, also, we've done a lot of work in the DSLs and other things. All the kernels can be used with all the sort of standard array interface implementations that you're used to, like DLPack and the CUDA array interface, et cetera. So everything just sort of works out of the box. You can also, today, you can interop in the same program with other CUDA code. So if you want to do back-to-back kernel launches, you can write a SMT kernel. This is one written in the NumPy CUDA interface, and then one in cuTile, and just execute them, back-to-back in a CUDA graph or in your model or something like that. Go a little bit deeper. I want to deep dive on and actually go through the kernel and explain how this maps to IR and kind of what the abstract machine of the language looks like. So here's what a matmul with a little bit more annotations look like. So the DSL does some fancy sort of staging and tracing stuff. So some of the annotations most of the annotations are not required. One thing to call out here is that we take, for clarity, I have them here. We have 3 input arrays, A, B, and C. There's no dimensions or anything annotated, as you notice. We'll talk about that in a moment. And then there's one constant time parameter here coming at the end, which is the tile size, which we're going to use to parameterize this kernel by a compile time known dimension. So the TileIR abstract machine, the semantics are actually relatively simple. There's global memory, which contains any number of allocations. This is global device memory. In this case, we have A, B, and C highlighted in green, placed in global memory. There's some conceptual code section. You can view this as the MLIR module. It contains the program text. And then there's n logical threads or tile blocks, each encapsulated in its own state. So each of these logical threads, we're going to talk about how they execute in a moment. The same kernel that I just showed you, this is the IR for it. So this is slightly cleaned up. There's some assumptions and some other things that the compiler will generate if you wrote this code yourself that I deleted for clarity purposes. But roughly it fits in a slide. So you can see that it's not, the correspondence between the DSL that we wrote and the IR is not, it's not a big gap semantically. So we're going to walk through the kernel. So here is ct.bid is the equivalent of like get the grid dimension. So in this case, it gives you the x dimension and the y dimension. That's the x block ID and the y block ID. And you can see that that corresponds to an operation that's built in called get tile block, which returns a 3 tuple that is x, y, and z. And then when we zoom in on one tile block, so we're going to zoom in on only one of them, you're going to end up with something that looks like this, where each tile block contains conceptually an infinite register file and its own program counter. And you are going to then, when you execute this instruction, you're going to end up with 0 and 1 in your infinite register file containing a tile with a single element. So this is 0 rank tile. And the important thing to note here is that everything must be a tile. So like all the values in this case are tiles. So even when you have a scalar, it's also a tile. So the next thing we're going to do is we're going to allocate a buffer for doing the accumulation loop on the MMA. And we're just going to pass the shape. Remember, this is a compile time shape that we talked about. And dtype, a.dtype here is also staged. So you can actually read this compile time, it will be computed away. So what that looks like in our kernel is that we're going to end up with a constant allocation here. So there's a constant operation. The constant operation says I want to initialize a buffer of type F32 with zeros, and it's going to be 64 by 32 by F32. And what that looks like here is that we end up with, in register 5, let's say, we end up with a multi-dimensional array, conceptually. This is like the logical semantics, containing a bunch of zeros. The important thing, though, is that it's like all tiles must be statically shaped. So that's one of the restrictions that we have in the programming language, is that the values are statically ranked and statically shaped, at least for tiles. And I'll explain how we deal with dynamic dimensions in a moment. So then we want to figure out, actually, given A with some tiling along some dimension, I want to know the number of tiles that I'm going to produce by doing an iteration across the dimension. The cuTile has a built-in helper called numTiles. This gets turned into some, like integer sign extension, division math. It's not super important to zoom in on, but we lower that away, and we can like stage and compute all that out. And then what you're going to do is you're going to pass that to the range loop, which in this case, if that number, and it is dynamic, you will then generate a loop that actually executes this reduction. So you can see that this actually gets realized in an MLIR loop. Like for those of you who are not MLIR folks, MLIR has sort of data flowy semantics where all the structured control flow constructs have to return their loop carried variables and values. So here actually, at the end of every iteration, you're just going to carry forward the immediate buffer. So the DSL will do this translation of this functional style for you, and you're going to get this behavior of carrying it. And you can see here that we're looping over the constant 0, to the k value that we computed, and we're going to step by 1. And we're only going to carry the intermediate accumulator buffer as the loop carried variable. So then what we're going to do is the matrix multiplication is super simple. We're going to load the x by k tile. We're going to load the k by y tile, and then we're going to do an MMA on it. So what this looks like when you get lowered to IR is we're going to run a sequence of 3 things that I'm going to dive into over the next couple slides. We're going to build a tensor view. We're going to partition that tensor view, and then we're going to load a tile out of it. And this is like the expansion of all of these load operations. And what that means is this sequence is how load is lowered. So remember, going back a few slides, the pointer, arg0 is a pointer, by the way, if I didn't highlight that in the previous slide. And that's a base pointer pointing to A in global memory. So this is a global base pointer. And we're going to pass that to make tensor view. What that does is make tensor view allows us to associate a potentially dynamically sized and dynamically strided volume in memory. So in this case, if it's like a 2D matrix, we're going to have arg7 in this case, which is the other argument that gets passed in that corresponds to the dynamic dimensions of the array. arg7 here and arg6, and we're going to end up with something like this, right? We've got a bunch of elements in memory. This is all in global memory still. And the only other kind of value type that we have are these views, and the views, though, from a dynamic semantics are not materialized at all. They're effectively a compile time only construct. So when you create this tensor view, you actually see its return type in this case has 3 question marks in it. It's because both of the dimensions are dynamic, and also one of the strides is dynamic. And this allows us to do the general purpose, like I accept matrices of any shape and type matrix multiplication. And we're going to be able to represent that here in this case. So then what I can do is I can take, and this is the key part why we need some amount of staticness in the language, is that what I'd like to do is I always want to do the dense innermost compute in statically shaped and statically sized things. So what I can do is I can create a partition view of it, which actually allows me to give a static tile shape, in this case 64 by 16, to the partition. And this allows me to then index into the global memory view like a bag of 64 by 16 tiles. So you can see, like in this case, I've logically put this view in the picture over it, where the 0, 0 will be the first 64 by 16 tile, and so on and so forth. And you can just now index into it like normal. So then when we generate code, I'll explain briefly for a second. One other thing is that MMA also in the functionalized semantics, it produces a new value. So you also have to pass the previous accumulator. So that's why we take A, B, and sum. And you can see now that the load is going to, the loaded values, and I'm going to talk a little bit more about it in a second, are going to flow into this MMA, and then we're going to produce that final iteration. And what we're realizing is this computation, right? Like we have the partial sum of xki, kiy, plus the previous sum of I minus 1. And the way that we can realize this is when we do the load, all we have to do is give the indices that we want. So it's a loop index and the extended value in this case, because the sign extension occurred. And we're going to get out the tile that we want. So you can see that when I do one of these loads, the partition view, MLIR is very weird. So you have to annotate the type of the arguments at the end, so it's sometimes confusing. The thing at the arrow is the actual return type. So you can see in here, this case, we're going to get back to 16 by 32 tile. This is the other load. And that will be the final value. And then all we need to do at the very end is store. And store has the same sort of expansion sequence, which is make a tensor view, partition it again into the appropriate tile size, and then just store a token back. Or sorry, store a tile back.
Two quick questions.
Yeah, go for it.
The previous slide, so we are essentially doing accumulation over tile to matrix multiplies.
Yep.
Basically. And then the expansion that you showed in the detailed form, is that the TileIR, this one?
Yes, this is the actual CUDA TileIR, like the MLIR intermediate representation.
And one can write classes over it also?
Yeah, so all of the currently, we've been talking about opening up more things as well, but I'm happy to talk about it offline with people. Right now, the dialect is open on GitHub, and so anything above this, you're free to do yourself. So you can, for example, the C++ compiler actually has a huge prefix pass where they try to take the C++ subset they support and like normalize and compute away a bunch of constructs so they can lower it to this language, because they support like, not quite full, but full C++, like structs and fields, and they're able to generate this from that language. So that's matrix multiplication, though, in summary, is you can see, like on the final slide, for all the dynamic arguments, they all got expanded by the DSL. we get this very simple loop that kind of corresponds to exactly what you expect, and it's limited to a small number of concepts. One of the things I want to talk about is part of the reason why we've done it these view way versus sort of, we also have a Triton style sort of array of pointers style APIs too, if you want to do like scatter gather style loads. But part of the structure that we've been introducing here is to make there to be more structure on the tensor programs, partly because they map better to things like the TMA, but by giving more structure. You can see actually we don't have to do much of what Triton does with like mask manipulation and predication. All that is hidden from you as a user, and we try to push those details like down into the like below the programming model so that they're handled by the compiler. So one thing I want to talk about is actually a very big departure from other things in the space, or I don't know if anyone else is doing this right now, is we have a memory model. And what we've done is all memory operations are actually unordered by default. So this is very different than what other people are doing. Often either they're ordered or they're underspecified. So one thing you can do in Triton, for example, is you can like construct programs where you observe partially written tiles, or you can race, and there's no real guarantees. The compiler has some implementation defined behavior that it respects, but you don't really know. So we moved to this unordered model. One of the less intuitive things about this is that if you want two memory operations to be causally linked, or like ordered with respect to each other, and then have like a causal order, is that you need to provide edges or tokens between them that link the operations. And the reason that we've done this is that this actually gives more freedom to the compiler as well, because we have scheduling freedom now, and we don't need to over-synchronize. You can imagine a very simple case is that if you want to guarantee that one memory operation completed before another, and you're working in an aggregate with a hierarchical memory system, I have to force everything to be written to memory and then conceptually sync and do either coherence or some kind of memory synchronization. And then I can begin computing on the next tile. This is horrible for parallel programming, because what we're actually doing when you do an MMA or when you're doing an element-wise operation, we're actually exploding that operation into maybe thousands of threads that are all individually operating. So you want to be able to reason about the behavior there, but also to have a sound model. So the memory model group at NVIDIA has done a lot of work. We have like a semi-formal one. I think we've stayed away from being very formal, because sometimes if it's very formal but not perfectly right, people ascribe too much correctness to it. But some people are working also maybe on doing a mechanized version as well. If people are interested in this, I think it's an interesting area, because memory models in this sort of aggregate computing world with concurrency and communication, and they're becoming very complicated to reason about. Another thing is, there's built-in auto-tuning. One of the things to get performance often is like that tile size parameter that I showed you before. You really need to auto-tune to get peak performance, and that kind of goes into our philosophical push, is that we've tried to create these axes of tunable hints, not just the tile size. There's also some performance hints which you can read about in the spec, which allow you to have control over the behavior, but without having to rewrite the core of the kernel. So kind of to wrap up on the front ends, so cuTile really is a family of programming language exposures, if you want to think about it that way. When we first released CUDA TileIR, cuTile Python was released with it in CUDA 13.01, which is December of last year. Earlier in the year, we released cuTile C++ a little bit after GTC, so about April. And then cuTile Rust is actually available on GitHub as a research project if people want to go check it out. And you can use it, you can write real kernels in it. The Julia community has done their own. And most importantly, the overall product lead for all of CUDA, Rob, for April Fools, had written Tile Basic. So you can take a basic program and translate it to TileIR. That's kind of a fun blog post if anyone wants to read it. But we expect more language to be able to easily kind of adapt to writing kernels. And I think that's actually one of the big motivations that I didn't say in this version of the talk, but is to make it easier for people to target the GPU from different programming languages. I think part of my perspective, at least, is that people are going to write more blended applications in the future. Like, no one is doing it quite yet, but it's likely you want to write a database that's running an LLM in a tight loop and you care about latency, or you run some kind of machine learning model. And I think as the programming models get more flexible, you're going to see more of this blended split execution. And in that world, people are going to probably be programming in more than one language. And this gives us the ability to expose that without having to rebuild all of the MVCC or some complicated new compiler technology. I want to briefly just talk. I'm going to kind of go over this quick, and we can talk more about it at the end if people have questions. So one big effort that we've been doing is actually making this programming experience native in C++. We recognize that even though all the deep learning people are all writing Python, there's a lot of C++ code still in the world, especially in HPC and other areas. And so we've made it native in C++ to write these tile functions. What you get, you can kind of see here, is that there's a new global attributes, CUDA style thing, underscore tile underscore. And this will kind of put you in the tile mode. Some new restrictions go on the functions that you can write, but otherwise you get all these native APIs. So you can write, autos work, and you can write ranges. So you can see that the kernel, sort of matmul, hello world matmul, or the softmax look very similar to what you would have written in Python, but you can now write this in C++, and it integrates with your build systems and your tooling and the other systems you're building. So we think this is a big ecosystem push, usefulness of just being able to co-locate this code in your existing C++ code. And like I said, there's a lot of equivalence with the Python code. One really cool experiment that people ran is there's some people on the cuSparse team have this sparse matrix vector multiplication that they wanted to try rewriting in Tile C++. This is what the kernel looks like. So this is like this LPAC algorithm, which is like a sparse matrix algorithm. If you're a sparse matrix person, you know more than I do. But they rewrote it this way. Before, they actually had 12 different kernels that they would try to auto-tune exhaustively over to try to find the good performance. And the cool thing here is that for some of these use cases, there's up to, I believe, 3x improvement by moving to TileIR just by rewriting it. And you can see it's not a lot of code. And the next slide actually is the interesting part. But it's the movement. The previous one was 1,035 lines of code, and they had to do the exhaustive picking. And now they get a reconfigurable kernel and 78 lines of code that they can then go and retarget to the new GPU or the new configuration that they have. You can also auto-tune over, et cetera. One of the interesting things is, to me, is just that so much of the fusion and memory operations, like if you actually talk to the folks building libraries, they haven't even, they're like, actually even in academia sometimes, people are still targeting A100 because, one, hardware availability, but the new memory abstraction has gotten so complicated to write non-standard matrix multiplication-y things for. People are not using them. Because like if I want to write a kernel that does something like this, I actually need to check all these conditions I was talking about. Like, do I fit in the TMA size? Am I in bounds? So you have to write this very funky one-off kernel that has a lot of preconditions on it. And if it doesn't fit, you still need to write the backup kernel or the backup end kernels. And I think this unlocks a lot of power in that way, where they can experiment with some of these new techniques all with one implementation. For example, the TMA selection is a hint that you can annotate on a single load and say, disable TMA, enable TMA. And now it's a simple experiment, or like an ablation study style experiment versus multiple months of rewriting just to not be able to get a result. So I also had an example on what it looks like in Rust. Here's a similar same gem if you want to look at it. And again, this is on GitHub if you want to check it out. One interesting thing that the paper talks more about is there's some safety design features that the Rust folks have been able to compile down to TileIR because they use the type system to prove or prune some properties, which is kind of a cool thing. So here actually the stores are safe. So like the way that you handed the partition to the store, you can only store back to the tile that you wrote. So it actually proves like a disjointedness property where you're not actually overlapping. Because all the kernels I showed you are actually extremely unsafe from like a memory safety perspective, like everything's mutable shared memory. So these are some cool things in Rust like this that are fun experiments. And this is the kind of things I believe that is useful for building or shipping these foundations is the community can experiment on top without having to recreate all the performance work above, and really play more with the programming model or the integrations of the applications without having to do all the work, again, for the millionth time. One other interesting thing to check out, just to plug, is we have many open examples of this, and actually now there's a lot of skills and agentic additions here that allow you to write and optimize kernels. So we have some people that have been just pointing at this and porting some of their kernels over and getting like pretty reasonable results just in like a one shot, in an afternoon with Codex or Claude or something. So check it out. It also just a useful guide for learning the language and seeing some different patterns. The important thing though is, like I've been saying all this, and it's like the so what is, can we actually provide good performance, which is what people are always asking. So this was about 3 months old now. So I think this is like March timeframe when I took this data. But this is us comparing cuTile kernels against Flash Infer, which is this, for those who don't know, is sort of the new bucket of very fast kernels written actually by another UW alumni who's now at NVIDIA and is working on this, that's being used in SGLang and VLLM and all of the serving engines. And you can see it like, we're not always faster, but like we're within that sort of Goldilocks range that we wanted to be, which is like 5 to 10% of SOL in NVIDIA speak, or state-of-the-art performance. And then in some cases, like on unique sizes, this is where the compiler approach really excels. There's always under-optimized data points where there's way larger gains. So they actually just merged the first cuTile kernel into Flash Infer this last week, where there's a few cases on H100 where it's 1.7 times faster than cuDNN. And the cool part there is it's an under-optimized workload, because the way everyone moves today, they just move to Blackwell, and no one cares about H100 anymore. But H100s, there's still hundreds of thousands of these chips or more out in the world that people are using. And I think this is where the compiler approach really starts to shine. And as we ship performance improvements, people get to benefit from them on every release. So there's some highlights here that I'm going to just skip for time reasons. So the final thing I wanted to touch on a little bit is, I think what the biggest challenge is that, so we introduced a new programming model. We have a lot of code that is written in the old programming model. What do we do? So one of the things that I've been spearheading for the last year is trying to do thread-tile interoperation. So the goal here is that you can define a new foreign function interface that allows me to call existing thread code, which is written under one abstract machine model, from the other abstract machine model, and then combine them in a way that is no cost. So this data is also a little bit old. I think we can get to exactly no overhead. But the cool thing here is we can call, so CUDA co-op is a set of libraries in CCCL, which is like the NVIDIA C++ standard library that people use. Here's also an FFT, which is in cuFFT. And you can see this graph, which is on the alpha version that we've built internally, is only 4% overhead. So the cool thing is, based on the design that we set up, we are actually able to pass the intermediate buffers even in registers. And then there's a zero copy overhead between calling from the lower level SymT primitive to the tile primitive. And we can now actually sort of like inline and co-optimize these units of code with it. And I think this is really big, because back to the hash table, or a great example is, I think there's a statistic that one of our architects likes to quote, like 40% of the compute time, or some crazy number like this, is spent in compression these days. People are doing compression everywhere. And so there's a library for compression called MVComp, but you're not going to write a compression library in Tile. Like you can see how awkward it would be to try to, all you have is tiles. It'd be awkward to write some Huffman encoding or something like that. So you can actually bind to NVComp and call it directly. So you could easily add it here, and we could write a kernel where we decompress, compute, recompress, store. And the same is true for sparsity, for random numbers, for FFT, and many more. So here's actually a really fun one. Comms actually fits in the same bucket as well. So this was another experiment we did around GTC, which is we are writing a 3-kernel distributed FFT. And so here we've got the 3 kernels that are doing one FFT. And again, if you're an FFT expert, I'm not, but I know enough to at least give the slide. You do FFT in the Y plane, you do FFT in the Z plane, you do some exchange data, and then you do the final plane. And you can see that each of the boxes here corresponds to one of these stages in the algorithm. And this is all that is needed to do the distributed version of the algorithm. And this is not even like the fully productionized version that there's still room to make the APIs nicer and everything like that. But this actually binds using the same interop mechanism to NVSHMEM, which is our shared memory library. And you can see that if you want right here, these are the NVSHMEM APIs that you can call. So actually someone generated, I think NVSHMEM has 3,000 APIs or some crazy number like that. And in one day with Claude or Codex or something, they just one-shot did all the binding work out of it. And so we were able to just do this in a day. And it took a week to benchmark it or whatever, because benchmarking is always slow. But it's that's the power we feel of this interop mechanism, is we can bring existing code into the ecosystem and unlock sort of new powers for the tile programming. And you can see that here in the this is the mean speed up. So the crazy part is the handwritten C++ version of this, when we first ran the first data, was slower. So we did this thing in a week. We removed all the C++ code. It's written in Python. It's bound. It's compiler optimized, and it's faster in this 64 node setting. I think finally, one of the reasons why things like this to me are so important, and I just want to emphasize, is that there is more and more communication. I think when Mary is talking about things being asynchronous, to me it has already happened, which is that there is no synchrony left. The only thing that's synchronous is the data path on a single thread, or very few things. And so we're in this world now where everything's asynchronous top to bottom. It's like I do asynchronous transfers at the inside the chip. I'm doing them from chip to chip on a chiplet maybe, and then because there's like NUMA effects now. Then I'm doing it at the scale up domain, like on NVLink for us, or the scale out domain. And you need to now understand where all of your communication is happening. And then to make it worse, people are being very clever, and they're doing all these fancy like one-sided put RDMA tricks and other optimizations to improve performance. And now you have to reason about this whole thing because you're running a program on 1,000 GPUs, or if you're training tens of thousands of GPUs sometimes. So really, to me, the big challenge for us and going forward with all of these is actually, I think there's a shift happening upwards where, to me, the next frontier really is not programming the single device anymore. It's the rack scale programming model. It's how do we program an entire fleet of these devices? Because if you end up kind of an NPMD style programming model, you might have many like programs running over some split of your resources that are all cooperating to actually achieve your application. And the programming for this is awful today. You set up your Slurm cluster, MPI, you write a bunch of different program fragments, you have some coordinator, you have to understand the different comms types, you have different transport types, you're in different clusters, you're in a different data center, the different chip. So I think all of these building blocks that we're working on the tile side, to me, are just the first layers and the first steps of trying to build abstractions so that you can actually reason about the whole programming system and spend less time fiddling with the 10 lines of C++ code to get optimal performance. Part of that actually, and the thing I'm going to close on, is that one of the biggest surprises actually that's happened is that we showed all this stuff to the math libraries folks, who are usually the most persnickety, hard to convince people to port, and they're all like, we're going to rewrite everything. And so that's like a really interesting push for us, because part of the interop machinery, which I didn't have time to talk about, is that we can actually dynamically specialize some of the libraries for the particular input sizes. So they've been building these in a much less principled way, let's say, that has been hard for them to maintain. And we think that is like a really big unlock, because what they've been looking for is dynamic respecialization. And there's a bunch of challenges with trying to do this today. Like you can ship a fixed menu of different problem sizes, but now your code size explodes, and you have instruction cache issues, or you can try to JIT them on the fly, but the JIT time is expensive. So we really see that this is like an evolution of not only how we're writing programs, but also how we're going to build libraries and ship libraries versus the sort of static fixed menu style that has existed in the past. So finally, just a little thing, like this is all really new. So I think when people saw the first thing we did, they've been asking, like, isn't this just similar to Triton? That's true. But I think in the next 2 years, things are going to look a lot different. So like we're, CUDA 13, like everything kind of happened in the driver. 13.1, we released a compiler. 2, we brought Ampere and Ada back online. In 3, we brought Hopper, C++. There's all the low precision stuff, so you can now write NVFP4 kernels. But we're working on other things like the interop I talked about, more support for stencils and HPC. So a lot of people are doing cool emulated FP64 as well. We're in 13.4, which is coming out in a few weeks. You're going to have native communications APIs built in. So all those load store APIs I showed you can actually work on shared memory buffers. So you can like map a region of memory and load and store from it, and it will broadcast or receive from people. And then another big one we're working on is trying to relax. We still have a power of 2 tile size restriction like Triton, and we're trying to relax this, which I think will be very useful for the stencils and the sort of non-DL workloads. So with that, here's like my install side, which I can go back to, and that's it.
Thanks, Jared. Excellent presentation. I have talked to Stephen before about the cuTile, and I have a major question that how can we understand the tile with the hardware concept? Will the tile bonded to a single SM or an entire GPC?
Yeah, so I think part of it right now is that you have control in some sense, because like for Blackwell, there's a 2 CTA mode, which is like a CGA level, GPC level construct. So in that case, like conceptually, it's like at least a CTA is the tile block mapping right now. And like we haven't discussed going beyond that yet. The idea is roughly that is your unit of schedule code that you want to think about. And it's where the hardware boundaries make the most sense. I don't know if you have like a particular motivation, or like you just want to know if it's going to be fixed, or.
Yeah. I just want to know which phase are you currently in, and I know that. Right
Yeah, so
now.
the 2CTA is the only one where it will be some sort of different because then you'll use the cluster machinery to run in that mode. But that's the kinds of things we want to abstract in some ways, because even though we're all used to programming on these things, it feels like the kinds of details that most people don't really care. Like, because the Ninja programmer kind of that we always think about will always want the Cutlass sort of abstraction probably, where you can effectively just write assembly. But for most people, they don't have that level of expertise, and so we're trying to help. For me, it's really addressing that part of the world. Like, even again, back to HPC or other folks, like most people are not even using state-of-the-art speed techniques right now. So how do we help them is really the person that I'm most focused on.
Yep. And another question is about the asynchronous pipelining. Does the users expect it to manage them and cuTile right now to make the schedule of prologue and computation and epilogue?
Yeah, so I didn't say this, but the compiler today does automatic warp specialization. So it handles all of the warp, like warp groups and synchronization and barriering, like all that is abstracted from you. You have some knobs that can control the strategy. Like that's actually where we've been talking the most. And if people have ideas or feedback is, how do we maintain an abstraction? Because I think people can think it's like corporations want everything to be secret for IP or that we're evil reasons. But I think a lot of it is we actually, when we've exposed things, people end up building against it, and we want to be able to have an abstraction that we can move people along without them building. So we're trying to negotiate as we're designing, like what can we expose to people? What kind of diagnostic information? What kind of controls can we give you? So like one. The TMA hint actually came out from someone wanting that, where they're like, oh, on really small tile sizes, I only want to use like my own vectorized loop code generation strategy. So like, can I turn it off here? And we're like, okay. Or like maybe you want to provide some hints on the barriering or the buffering. So we've been iterating on the design there. So if you have ideas, well, I'm happy to talk about it. But today it's managed for you by the compiler.
Okay. And another question is about the localities between different tiles. It might be some data entry used between different tiles in a different pattern. Does cuTile right now have some analysis on that, or some profiling guided optimization on that?
So you mean in terms of deduplicating if I'm touching the same chunks of the tile, you mean?
Yep.
Yeah, so today it's the internal analysis will like deduplicate and relay out convert where necessary. So if you have like aliasing or you're like mutating, you need different copies, like all the spilling and management of the tile is happening inside the compiler. And those are the kinds of things that the annotations you might be able to give us more information. So today, if you provide some of the assumptions, so I didn't show them today, but there's a bunch of assumption language where you can put boundedness or other conditions on some of the variables. The analysis engine will like respect these and transform your code appropriately.
I see. Thank
so
you.
Like if you have conflicting memory rights or whatever, we will like synchronize, or if you know that you need 2 copies, we will duplicate. If you can't fit into SMEM or RMEM, we will cut the program and slice it for you. Things like that.
Okay, thank you.
Hey, Jared, great talk. So one of the things that always comes up with new abstractions is that you sometimes shift around the burden of performance. And in this case, it seems as though, based off some of the diagrams, that instruction scheduling might be a bit of a harder challenge, or static analysis in the compiler backend has a much greater burden on sort of peeling back the abstraction layers. Can you sort of convince us as to what things NVIDIA is doing to peel back those things such that if I don't write one of the like top 10 most common kernels in the world, I'm also going to get pretty decent performance using cuTile?
Well, so the way that I think about it is like, and this is like my 10-year summary of all this stuff. It's like with Halide and TVM in some ways, like a lot of the auto tuning we're doing was recovering a schedule that reverse engineers the cache policy. Like a lot of the tiling, or at least for like GPU stuff. It's like you're just trying to figure out the cache policy and like where the cache is. So I actually think that this is the same thing, which is the main job of the compiler is to take memory movement away from you. And that on the compute scheduling side, like there's still gonna be challenges, but I think one, for anything that's really important like MMA, it's gonna be built in. And then I think the interop is actually the way to address this is that if there's any computey thing that you wanna do, you have control to schedule that sequence. and then we take care of the memory movement still, because the memory movement is the hardest thing for users to deal with, and it has to change whenever any fact of the program changes. Like if you change the tile size, you often have to redo the whole memory pipelining, and this is why I think moving that job into the compiler to me makes the most sense, because the burden is very high. Like, if you're NVIDIA and you have hundreds of thousands, millions of lines of library code, like doing the rewrite is literally a nightmare. And I think that's the way that I've convinced myself, at least, is that taking away the memory pipelining seems okay. There's probably a little bit of performance left on the table. Some of it we can recover from hints, but also, again, I think the common case is most people are already not near the roofline anyways. Yeah. So like that's why I think there's maybe always room for the Ninja. At least that's how we convince ourselves. I believe is like there is room for the Ninja. I want to handwrite NVVM code or whatever. But the memory movement is my strongest argument to myself.
Yep. Thank you.
Thanks for the talk. I'm curious, with all of the different programming models proliferating for GPUs, is there presumably something other than the sort of TileIR that you're talking about, some other abstraction, which is I want access to everything, please. I'm a masochist. I want to destroy my brain with gobs and gobs of memory movement, but I want to hit the roofline.
Yeah, so today...
Is that CUDA, effectively?
Well, yes, and like you can always write it yourself, but I think what the closest thing today is QTSL, which is a staged metaprogramming abstraction over assembly, if you want to think about it this way, where if you download the version we have today, all the NVVM, which is like the LVM variation, like variant of NVIDIA's LVM backend, all the instructions are actually exposed to you, and there's some work ongoing that is going to be like people are working on building a plan around to expose it in a more first-class way and kind of continue to improve the Cutlass programming experience. But the idea there is like you can do whatever you want. Like it's you have full control, and that is like the brain bleeding version, if you will.
Does that have more than CUDA then?
Well, think about it as like a imperative language with all the intrinsics exposed, like in a structured way with a type system. So like like there's things that aren't, you could call right inline assembly to get access to, but are not necessarily like C++ constructs, like the barriers and some of the named barriers and things like that. All of those are going to be exposed in that world, or that's the plan, at least.
Got it. Thanks.
Thanks, Jared. Could you elaborate a bit more on the auto-tuning for cuTile? You mentioned block tile sizes. What else? What type of other auto-tuning it does?
Right now, nothing super complicated. I mean, really, like the tile size and a couple of these hints are the main tuning axis. I think this is part of the discussion I was addressing. The first question is understanding like what other things we want to tune, or like what. So like, Triton has a different set of tuning knobs than us. For example, they rely way more on software pipelining, so people often tune the number of pipeline stages. Like we don't have the exact equivalent, but we also have I always flip them for some reason. We have a latency hint and a occupancy hint, which are new tunable axes. Like latency allows you for any memory instruction to try to estimate the DRAM traffic at the time, like the sort of the real dynamic DRAM cost to kind of address Ryan's question. Like that actually can represent the last 10% or like another 10% difference in scheduling. And then the occupancy is also, am I the only one running on the GPU right now? So we have those are just examples of ones that we've exposed. We've talked about adding more. I think roughly because I didn't say this very loudly in this talk, part of the design challenge is that we are trying to build a forever portable abstraction, so we're not allowed to break anything. So we've been very conservative with what we have exposed, so that we have ideas, but like if there's something people really want, user input is really valuable, and it's been guiding some of what we're doing.
Thank you.
Sorry. Thanks for the presentation. Maybe I missed something during the talk. I'm curious about how token works. So for example, do you have two memory access to the same array? Can the compiler detect the dependency and try to insert a token?
It's sort of an up-leveled version of, so the p-text memory model has this morally strong idea, which is if it defines some conditions where if these things hold, then it's safe to race against a set of addresses. We have the same sort of idea, which is if two things do not alias, there's no overlapping, and you issue weak, unordered memory operations, it's sound. If you don't, it's undefined behavior. So if you know that they alias, then you need to connect them by an edge, and then the synchronization that's implied is computed by the strength of the memory operations like weak, acquire, release, etc., the scope at which you're executing, like tile block, device, GPU, or system GPU, like one is like everything on the NVLink domain, one is just a single device. And that then implies what fences and barriers we have to insert. Because like, for example, if you have two things that are fully aliased and you need them to be like strongly ordered with respect to each other, and it's at the system level, then we must do like a sys bar, like all memory subsystems have to be synced. This is horrifically expensive. So in the case where they're weak and unordered, then we don't do any synchronization at all. Any memory synchronization.
All right. Thanks.
If that makes sense.
All right. I think we don't have any more time for any more questions. So thanks, Jared, for a great talk.